Alright, so we are ready to start. Today is a full day, right? Most people still arriving, but let's, without further delay, it's great pleasure to introduce to you Antoine from Basel, Switzerland. He's going to talk to us about finite simple groups of the real Cremona of rank 3. Right?
Thank you very much, Lisa, for the invitation, for the opportunity to have my first time in Brazil. It's great. And to talk about that project which I really enjoyed working on. I hope I can talk about the same thing in Miami. But anyways. No. Okay, cool. So I think the audience is rather wide, so let's recall the basic definitions. Okay, my best friend here is defined like this. So this is the Cremona group that for now defined for any rank in any dimension over a field K, say of characteristic 0. And this is a set of rational the motivation for studying structure. So you take the automorphism of K algebra of this. This is a very old and extensively studied object, and this is very crazy. Like it can be, it is huge. There's no control on this group, and one way to understand its structure is to look at its subgroups, and in particular, its finite subgroups. Okay, let's start low and classical. Well, in this case, you just get PGL2, the automorphism group of a projective line. And finite subgroups are either cyclic, hadral, I include Z2 square in hadral groups, A4, S4, or A5.
The subscript here is P for line. Is P?
No, it's any
Okay.
positive integer.
Alright.
Okay. Any integer, non-negative. Okay. This dates back line. And the problem already becomes difficult starting from dimension 2. And the standards, I would say, are further work of Bertini in 1877, and much later, the proof being finished by Bailey-Moville. In 2000, who classified subgroups isomorphic to C2 up to conjugation. So I'm going to say this a lot. There are two levels of how to look at this problem. You can just ask yourself if something admits embedded into the Cremona group. So you're looking for conjugacy, for isomorphism that's in the groups inside this, or up to conjugation, which is harder.
Sure, so the group is isomorphic to some finite subgroup. To the Z2.
Z2, sorry.
Okay.
And as I'm going to explain, it's equivalent to classifying involutions on rational, variable involution on rational varieties. Okay. Then you have the work which I will go. 2006. He classified million subgroups. Finite. And what's considered as the standard is the work of Lugashev and Miskovsky. As well. Okay, publication I think in 2009. once the lecture was here, and he was not happy when I put the archive date. He wanted the publication date, so let it be. All finite subgroups of CR2 of C, and I will put quotation mark at all because people keep working on it a lot. So there are a lot of things to be done up to conjugation if you look at conjugacy classes and subgroups, and some things to be done for isomorphism classes as well. If you know a bit of how it works, it will be classifying the isomorphism classes of groups, but conic bundles, this is missing. Okay. So today I'm focusing on simple subgroups. So I'm not yet over R, but let's mention simple subgroups that occur here. In dimension 2, okay, in dimension 1, here it is. I'm only outlining the non-cyclic simple ones. Here, what are the non-cyclic simple subgroups? You will have A5 again, A6, and BSL27. We know they are conjugacy classes. And don't worry, there will be some geometry. It's not a purely group theoretical problem. Here you have 3 of them. Here 1 of them. Here 2. Which are represented by actions. And I will tell why I'm talking about actions. This one on P2, on the petal surface of degree 5, and on P1 plus P1. Okay, this is for A5. This one only on P2. And this one here on P2, and on the petal surface on degree 2, which is the double cover of P2 branched over the kleine quartic. Yes?
Two questions. So this is
PSL27.
Yeah, what is this?
It is the project. So you take S cell dimension 2 over F7 productivize. Okay.
And when you say the atom space, it means as automorphisms of the space of P2 the best.
Yes, I'm going to give details for this. Absolutely, that's the point. So we start with birational maps, and we have a process called regularization, which means that instead of considering birational maps, we consider irregular maps on some rational varieties. Alright, dimension 3. Well, this is why I deal with it, but I will mention some existing results. First of all, I'm not going to give details, but there is recent progress on this for a Lobinov, Jean, and myself. 2025. But the only, say, well-finished classification would be that of simple groups. Given by Gromov. In 2009, and yes, what I wanted to say also that I forgot is that this group here is so monstrous that we had a motivating question of cell. Which was whether any finite subgroups, finite can embed into Cremona. Did he ask it for rank 2 or 3? Okay, anyways, let's say rank 3. And until the work of Gromov, we didn't even have an answer to this question. That's why I'm mentioning this now. So, in particular, he proved that the answer to this is no by showing that the only simple subgroups that occur in Cremona 3 over C are the following: A5, A6, PSL27 again, and 3 bigger groups: A7, SL28, and PSP4, 3.
May I ask if there is a clear relation between, for instance, number of connected components and the subgroups?
Oh, the Cremona group?
Yeah.
So, I'm not an expert in non-finite groups.
It's alright, it's just that I want to, I don't know.
Now, question about it being disconnected.
Sorry?
Is it actually disconnected?
I don't even know.
I think that in some language.
That's the work of Ludmil saying that it's not topologically simple, I think. Yes.
Perhaps can I ask also, what is the motivation behind this question by Sarah? It seems rather arbitrary.
It's made like glove.
The question was asked after the problem.
Can the group be a glove? It's very similar. And research spent lots of time.
Yeah, sorry. Okay. This guy here, A5, has been extensively studied and has many conjugacy classes, infinitely many. This one conjecturally has finitely many. Question mark, it's conjecture. This one also. And the three big groups have been classified as conjugation by Gromov. So this one only acts on P3, it has one conjugate class. This one acts on also only one conjugate class. Here it has one conjugate class and acts on so-called Gromov's threefold. Okay, I will write it here explicitly. It is Lagrangian Grassmannian for 9, then that intersect with an invariant 8-dimensional prediction space inside peak 15. Okay. And this one here acts twice, it has two conjugate classes. One on P2, P3, and one on Burkhardt quartic. Which is the following. Supporting P4. Okay. And I want to add about A5. Just to emphasize that it's totally out of control, even despite a lot of work. There's a whole book about this one. Just about the conjugate classes of A5 and Cremona 3. It's called Cremona groups. And the icosahedron. Like Jetsov and Schwahn. Alright. So now I have talked a lot about group actions, but I didn't even say why. And now we switch from a purely group theoretical question to something more geometric. Through the following method. We need the notion of G-variety, which I think was introduced by Manhã. I need projective variety X a group G and an injective group morphism from G and the automorphism group of X. In other words, G acts faithfully biregularly in the variety. Okay, I need the notion of G birational map. This will be a map between two such objects. With the same group, different action, which is birational between X and X prime. such that it works well with the group action, in other words. Phi rho of G phi minus 1 is rho prime of G. And third point would be that if, it's just a bit of jargon for the theorem that follows, if such a map phi exists, x and x prime are called G birationally equivalent. Sometimes you say birationally conjugate. And I will denote like this equivalence relation. And the punchline that allows us to work with these objects is the following. On one hand, you consider, let's say, finite for my purposes, finite subgroups of Cremona on the other hand, rational meaning there exists a birational map between the variety and the objective space. Rational G varieties of finite group actions. On one hand, you quotient by conjugation, consider the conjugacy classes. And here you quotient by this equivalence relation. And this is in a one-to-one correspondence. So, instead of considering birational maps, I consider biregular maps on some wider class of varieties. As we can... No, sorry. Questions?
Yeah. Why, if you have a birational map, you need to find a model for which, a birational model of your manifold where this group acts regularly. It's not obvious that it exists.
That's not obvious at all. No, that's a theorem. It's actually wrong for general groups. It's true for finite groups, it's true I think for algebraic groups, but say for example, dimension 2, if you take a group that strictly, a subgroup of Cremona that strictly contain PGL3, you will not be able to find regularization.
But the regularization is just like equivalent to blowing up the indeterminacy law, right? I mean,
Yes.
Just that, right?
Okay. So now we have rational varieties, and we want to refine them. We want to restrict to some classes of variety that on which we have more information. Okay, so this is where MMP will help us. And long story short, it means that we may assume if I call these guys X, that X is a G modifiable space so there's a bunch of assumptions that sometimes I may forget some of them. but X has to have terminal singularities. Has to be Q factorial. And also there exists a morphism from X some base B, surjective, with the dimension of B strictly smaller than the dimension of X. Minus AX is relatively ample, and we have a crucial assumption on the rank of the invariant part of the Picard group. Sorry, this morphism has to be G-equivariant in this context. This will be 1 plus the rank of the invariant part of the Picard group of B. Did I forget something? Yes, I did. Fibers are connected. In particular, you may notice that if B is just a point, then we get a final variety. Which we will call G final. Okay, and today I'm talking about simple groups. So we can make the following remark. This structure here gives you the following exact sequence. When you have a group G that acts on a modifying space, on a G modifying space, it gives you.
So Schwahn in your version has only Picard 1, right?
Yes, I should say minimal. Yeah. It's called, if you wish, minimal G-final, that's true. Usually when I say G-final, I include minimality in my mind. KGH1, this guy acting on the fibers, and this one acting on the base. So, I put quotation mark because sometimes there's still something to do, but essentially, for simple groups, we may assume that X is final. Why? Because if you have a non-trivial fibration, you split your group. Okay? And for simple groups, that will mean that either G acts faithfully on the fibers or on the base. So basically you downgrade the problem by one dimension, by at least one dimension. And then you refer to other people's work. Yes?
When you write MMP, this is G-equivariant.
Yes, absolutely. G and MP. Okay. groups. So, purpose of the day, finally. What about, I will speed up a little bit, k equals r. Okay, dimension 2. Okay, dimension 1. No non-cyclic finite group. Simple group. Finite, simple group.
Sorry.
Yes.
This G and T is only for finite groups, or interesting?
Let me be careful about this. It is at least for finite groups. Let me be careful. Okay. There's a nice survey of Gromov about all these things.
From which year? This year?
Recent. Recent. A few years ago. Okay. Dimension 2 over R. You have only only A5. No, only A5. What am I saying? Only A5. Yes. Only A5. Still with 3 conjugacy classes. Now you understand why I was representing conjugacy classes by actions and varieties. You still have P2. You have P1 cross P1. Or you can say a sphere, okay? Conic with a point, with a real point. Or the Bezo surface of degree 5. This is the only one, and that's a corollary of the work of Igor Biasinski. Okay, a few years ago, rather recent. Okay, and dimension 3, finally. That's the theorem of the day. So I don't have much time left, but anyways, the full proof is out of reach in this amount of time, so I will try to make you feel where the difficulties, where the problems are. I will make a map of the proof, but if you want details, we can discuss, of course. So by Chekhov, Gromov, and myself in 2025. Yes. Fun project which was split between Marseille, Turkey, and New York. Okay. Non-cyclic finite simple subgroups of Cremona 3 over R. R. A5 and A6. And that's it. We expected to exclude the big groups, but for PSL27 it was very tricky, and even if you look over in dimension 2, there is still PSL27. So that was really the mysterious part of this project. So a very small part of the proof that I can do is to see with you that the two groups here indeed act. I'm giving you examples of actions. Okay. A5 will act on what, P3. A quadratic with the points. P1 times a quadratic with a point, quadratic surface. And a sacred cubic. This one I will detail it later. Okay. Aces. This one is less straightforward. Oh, there are others. This is not finished at all. We don't know the rest of continuity classes, but we know there are distinct. A6 will act on the sacred cubic as well, and now I'm going to detail it. This will be given by this and that inside P5. And as I said, we're working with rational varieties with group action, depending group incremental. Why is it rational? Well, this is something you can see from starting from P3. You blow up five bones in general position. You obtain some variety from which you contract um, 10 lines passing through pairs of points among the 5 points. And like this, you open X. Oh, we need an action, of course. Probably you can spot an obvious action made of even S6. Okay, the equation is very symmetric, you just plug in the coordinates. So you put the positive part of here, the group that we put here. And the crucial remark for the group that we don't get, it's obvious but it's crucial, is that Cremona of R and its inclusion Cremona 3 of C, and we refer to, okay, it's erased now, so we have to just pick the 6th group of Gromov. For 2 of them, we found an example, and for the other 4, we need to exclude them. So, now the next part of the proof will be given by answering, by proving the following proposition. Let X be a real rational threefold. G be one of those groups, then G doesn't admit an action on X, a faithful action. When I say action, I very often think faithful. And anyways, with integral groups, it's either faithful or trivial. Okay. Oh, 6 minutes, okay. So, these three groups, I will call them D. So when I say G is big, it means G is among those three. And here's the map of the proof, which is the best I can do in this amount of time. This project is basically, okay, even without counting the positive, the existing examples part of the project, the project is split into two parts. G is big, or G is PS7 to 7. Then we have subcases here. X has corresponding singularities. And here it doesn't. And we have some cases again here. One is when the anti-canonical linear system is non-empty, and one when it is. Okay. This part here is okay, there's work to do, but basically we use Gromov list of group actions on complex modified spaces, and we refine it a little bit. This here is the bad case, because Gromov didn't classify anything for this group. If X is Gorenstein, there's a lot of previous work. We call it the geometric case, and we have the notion of genus. We exclude a lot of possibilities for the final genus. It's not too bad. The, say, bad case is this one, which is split again in two cases. In this case, either we have a big dimension for this linear system, in which case you get a map to threefold, which ends up being Lorentzian. So we get back to the formulas. And so I'll write it like this. One can relate And when the dimension is small, you have a lot of invariant surfaces in this linear system, so invariants always give a lot of informations and abstractions. And here, what I would call bad is this side. This was totally uncharted. We have some control, like in the number of singularities you can get using Riemann-Roch, orbifold-Riemann-Roch, and you can also consider invariance in twice this anti-canonical linear system. But this was really the hard part of the project. So what we did is that we started from this, and when it was solved, it kind of gave us hope for the remaining part, for all the rest. Okay. So, okay. I will finish by just illustrating why this group was so mysterious, even after working on it for a while, and even after some people working on it too. We had like some sort of bets between the three authors, whether this group existed or not. Some said that it wouldn't exist, some said that it would, and we ended up finding an example of a complex rational threefold. I'll state it as a final remark. Which we can attribute to Terpo and Zimmermann. You consider the threefold, which is given by x0, y0. You basically take the 1-1 divisor in P2 times P2 plus x1, 1, y1 plus x2, y2. That's a complex threefold. Then this guy admits a real form. With an action of PSL27, which just this is difficult to find. I mean, it wasn't obvious to us. This is a rational threefold. But its real form, say Y, which has an action of this group, is not actually not rational over the ground field, over R. So we just miss the last ingredient. I mean, last but not least, it's very important. Yeah, I hope that gives you an idea of how this project was really on the edge for quite some time when we were thinking about this group. This was really the tricky part. Okay, I think I should stop here. Thank you.
Are there questions, comments?
Can you get a question?
Sure.
If you have a hypersurface, Pn, you look at the partial derivatives, and that gives you n plus 1 homogeneous polynomials, which you can think as a map, a rational map from Pn to Pn. Right? Maybe not Cremona, right? Because we don't know if it has an inverse. But is there any relation between properties of the hypersurface and this type of Cremona? Are there Cremona transformations that are partial derivatives over the polynomial.
I never thought about this way.
Okay, so I guess my question is if there's a literature, if you know literature about
I don't know.
if you apparently don't. Thank you.
Other questions?
So, if you want to go to BL4, so the technique would be before to classify planets of groups in C and then come back to R, or is there another?
If I want to go to what?
To dimension 4.
Okay, definitely we start with C, if that's your question.
Okay. Do you have any expectations?
Even in dimension 3, we have we are very far away from classifying all the finite subgroups. If you restrict to the simple groups in dimension 4,
And is it out of reach or?
for now they are out of reach. Yeah. The first step would be to see what simple groups act on fan of faults, okay, which is totally unknown. But one might have some surprises. Like, it's not obvious that we will get many more groups. Like, even if you just consider P, on the level of biregular automorphism of the projective space, there are fewer simple groups acting in dimension 3 than in dimension 4. There are less simple groups in PGL4 than in PGL5. Well, in Cremona, I think it will definitely increase. How much, I don't know. Dimension 4 is like completely open when it comes to finite groups.
Other questions?
Yeah. So what about automorphic other fun? For instance, there are certain K3s associated to fun, this fun associated to K3, so can we embed automorphism of K3 to the automorphism of fun?
We can extend them.
Oh, yes.
That's a very good question. That's a way to proceed when you want to build or construct automorphisms of Fano varieties. You may look at invariant surfaces in the anti-canonical linear system. I think that's what you're talking about. And so you have your group induces an action of a K3, and you extend it to get an action on all three folds. And indeed we use this process a lot. Not much in this project because we rely on Proffler's work, but he does this in his paper. And on my project, a billion groups with Loginov and Jean, we use it a lot. We even name some groups of K3 type. They will be by definition the group that are extensions of group acting on K3 by a cyclic group.
So I'm sure that if you have a finite subgroup and automorphic K3, it acts on the sign.
Sorry, say again?
So suppose you have a finite subgroup and automorphic K3. Will it act on the corresponding fun?
Not always.
Not always.
Not always.
But
sorry.
Can it have big automorphisms of fun, like, because automorphisms of K3 are really big, it's really big.
No, sorry. This automorphism group of a K3 should act on the fun. I'm thinking of extensions. The tricky part is to know how to extend it to get the possibilities on the file. Thank you.
Any other questions, comments? Maybe I just would like to say I went to check, and indeed the Cremona is always connected for any grid equal than 2. This is resulted by Blanca.
Okay, yeah.
So
I wasn't sure.
connected, yes. So let's take that one once more. So we resume the 10 minutes.
Yes.
Okay, and we go to the ways. Feel free. Alright, so we are ready to resume. It's a great pleasure to introduce to you Schwahn from Unicamp. He's going to speak to us about the geometric connections with the parallel and closed skew torsion. Please.
Thank you, Leonardo, and thanks to the organizers for giving me the opportunity to speak here. I'm going to report on very recent work that's joined with Andrei Moroianu from Université Paris-Saclay. So, as you may have seen in the abstract, I will split this talk roughly in 3 parts. There's a very interesting class of geometries, at least in my opinion, which are those with parallel and skew torsion. I will first recall what they are and give a few examples to motivate the whole thing. And then we're going to introduce the additional condition of the torsion being enclosed, say explain the classification results in that table here, and then we're going to talk about G-structures that live on certain geometries. So just to define what I mean, a geometry with parallel skew torsion, which I will abbreviate henceforth by PST, is a Riemann manifold called M and G, together with a connection, with a metric connection, nabla, whose torsion, you guessed it, is skew symmetric. Torsion T is totally skew symmetric, so that means we can think of T as a free form, right? With that I mean we can always identify vectors and covectors with the metrics, so this thing here is the free form means that the torsion to one tensor has this symmetry here. And there's of course a minus sign here. Right, so we can not only interchange x and y, but also y and z to get a minus sign. But also it should be parallel. Lambda t is equal to 0. So some notation that I will be using in this talk. I will denote these geometries, these connections, by number tau, where number tau is number g, the Levi-Civita connection, plus some free form. So tau is in omega 3 of m, and the relation between tau and the torsion is simply that the torsion of the connection is 2 times tau. Writing it this way makes it a bit nicer in computations because you don't have to carry the factor of 2 or 1/2 around. This is meant to be understood in the way that if we plug in the vector x and we differentiate some tensor field alpha, say, then this is the same as number gx alpha plus tau x. So we plug in one vector here, we get a 2 form, understand this as a skew symmetric anamorphism, and then we use this diamond action to apply it to alpha. So it's the infinitesimal action of SON on tensors. Also, if we have 2 such geometries, so remain manifolds with a connection, then we're going to write this symbol here for locally isomorphic. Because I'm going to make a lot of statements in this talk which are of purely local nature, so that means that we can always find some small around every point we can find a small neighborhood which does that we want. So we don't want to classify these things globally, but at least locally we want to really understand them. And sometimes you get a sort of local to global results, but yeah, not always. Okay, so why do we care about these things? So they often come up in interesting situations. To give you some examples, some manifolds with Killing spinners. Not all, but some that we care about. So that's nearly Taylor in dimension 6 with nearly parallel G2 manifolds. There's Sasaki manifolds and free Sasaki manifolds. They all have Killing spinners and they all have a canonical or characteristic connection with parallel symmetric torsion. You can also slightly generalize those two and introduce a bit of scale and some parts of the metric, which leads to alpha Sasaki or 3 alpha delta Sasaki manifolds. Second is in homogeneous geometry, there are naturally reductive homogeneous spaces. Reductive homogeneous spaces. So what does that mean? We write our manifold as some quotient of Lie groups, and we assume that the Lie algebra G splits into the Lie subalgebra H plus some H invariant complement. So this is called a reductive decomposition, and M is called the reductive complement. Such a decomposition is not necessarily unique. We're going to see that in a few minutes, but assume that we have fixed such a decomposition. So this gives you a canonically defined, canonical, reductive connection on the homogeneous space with the property, so it has, you can write down explicitly what the torsion is. If x and y are in M, which gets identified with the tangent space at some chosen base point, then you can write the torsion of this connection as minus the Lie bracket of x and y in G, and then projected it to M along this decomposition. Oops, and you can also write down what the curvature is. R x y z is minus, we'll have this over here, R x, y, z is minus, so what do? We have two nested brackets. Again, we take the Lie bracket in G of x and y, but now we project it to H, and then we take the bracket of that with Z. Now we don't do projection because H acts on M, so this again will be in M. So this is the torsion and the curvature at a single point, at the base point. And these are invariant tensors, so these expressions define these torsion and curvature tensors everywhere in the manifold. This canonical connection also has the very important property that every tensor on M, which is invariant, is parallel for this connection. So in particular, we have that the torsion and the curvature are parallel. Now the question is just when is the curvature skew, and we take G to be an invariant metric such that, well, basically we want exactly the condition for T to be skewed. So this is that condition here. If this is satisfied, then we call M, G a naturally reductive homogeneous space, and then it is really the case that the torsion tensor is skew, so Mg tau would now be 1/2 T is indeed a geometry with parallel skew torsion. So these, is a large class of homogeneous spaces which is still not completely understood, but there has been great progress in understanding. As a special case of these, I'm going to show you some spaces where this decomposition is not unique. And then we actually have a family of connections as a result of this. These are called the Schwahn connections. Schwahn connections. So where do they live? So we fix G compact Lie group and lowercase g a y invariant metric on the Lie group G, and we define sigma x y z as the canonical free form. So it's basically just the Lie bracket reinterpreted as a covariant tensor. So this is for x, y, z left invariant vector fields on G, so this gives a tensor on G. So sigma is a free form because the metric is binariant for the Lie bracket. In fact, this is a left invariant free form, or a right invariant as well. And then we define blah blah with the parameter t attached is the Levi-Civita connection plus t over 2 times sigma. So this is, of course, a connection with skew torsion because it is of this form. Just take tau t over 2 sigma. And in fact, the torsion is parallel because, because this is left invariant, and these things are in fact the canonical connection for a particular choice of reductive complement. If we write the manifold, the homogeneous space as G cross G modulo the diagonal, you have a one-parameter family of possible complements you can choose. But yeah, if you just want to explicitly write down the connection, here it is. So these are these have parallel skew torsion. Actually, actually, I want to bring your attention to the case where we take t plus or minus 1. Here it actually turns out that number t is flat. And yeah, which connections are those? Those are the flat tangent connections or plus minus connections. And they have the property that nabla minus 1 parallelizes the left invariant vector fields, and nabla plus 1 parallelizes the right invariant vector fields. Right invariant vector fields. Yeah. So these are two particularly interesting connections. So you can do a similar thing. So this is on the complex group G itself. You can define a similar family on the non-compact dual symmetric space to G. Basically, you have the same reductive decompositions. You can write on the same family of connections, essentially. And also just on the Lie algebra G itself, thought of as a Euclidean space. And it turns out that here you do not get any parameters for which your connection is flat. The flat connections, you only get them on the D group. Of course, for t equals 0, you get here the Levi-Theta connection, which is flat on the Lie algebra. But if you want to have torsion, then only here on G you get a flat connection. So these are sort of elementary examples in homogeneous geometry, but I just wanted to make sure that we all have seen them because they will become relevant. Okay. So what's next? So these are just some examples of geometries with colors and torsion. There are many more, but don't have time to talk about all of them. What I do want to talk about is some structural results about these geometries. So, properties of P geometries. So if mg tau is PST, then we have that the holonomy group of this connection is contained within the stabilizer group. So we think of this, which is we pick a point on the manifold, we assume it's connected if we want. So all holonomy groups are the same, essentially. So the holonomy group at that point is contained in the stabilizer group inside On of tau. So tau, the free form at that point, so we can identify the tangent space from Rn and take a stabilizer group of this free form. Why is that? This is simply because tau is parallel. So this is pretty straightforward. Another property is that the curvature is pair-symmetric of this connection. So pair-symmetric means that we can think of it as a section of sym2 lambda to Tm or T star if you want. And this implies actually that the connection with torsion is an so let me write down. If the holonomy is contained in some Lie algebra H, then this connection on the tangent bundle is an instanton for this Lie algebra. Right. So, for some deeper.
What does this mean to be an AG?
What does it mean? Yeah, okay.
Oh,
Sorry. Yeah, I should explain that. So the thing is, so instanton basically means that the first two indices of the curvature tensor, that they say the orthogonal. So if we think of the curvature as an operator, as a symmetric endomorphism on lambda 2 Tm, then we want that everything which is orthogonal to H, we think of H as in SON, so it's in lambda 2. Lambda 2 is H plus H perm, and isoton means that the curvature operator annihilates H perm. So why does this follow from the passive metric? Well, since the homology is an H, so this is an H connection, this means that the last two indices, so if you want the image of the curvature operator is in H, and because it's symmetric, the curvature operator self-adjoins, so this means that it annihilates the orthogonal complement of H. Right? Okay, for some deeper structural results, so there has been a foundational paper of Andrei Moroianu and Zimmermann in 2021, and we have upgraded that recently, or generalized that. So the result is as follows: there is a reduction principle for these geometries with parallel torsion. So fix some intermediate subalgebra between the homology and the stabilizer subalgebra. So this is the Lie algebra that annihilates the three-form tau. So this is, think of these as subalgebras of SON, where n is the dimension of the manifold. Then ng tau admits a foliation with totally geodesic leaves. Totally geodesic leaves of the following form, or let's say the leaves which are locally naturally reductive homogeneous spaces. So this is where this example comes in. And if we sort of quotient out these leaves, or if we look at the local leaf space, so with local leaf space, if we call it n gn sigma, also a geometry with parallel torsion, and this geometry has the nice property that it actually is reducible in the sense that it splits into a product of H of stabilized and reducible geometries. So let me say the leaf space is T and reducible, i.e. n gn sigma splits as a product of mi gi sigma I, such that the stabilizer of sigma I acts irreducibly on the tangent space of T and I. And this whole thing is built together to ng tau. How are these spaces in the sigma related to the torsion? We have this master formula that tau is tau of the leaf plus the pullback of the torsion base, and then there's a mixed part which is given by minus A, where this is the O'Neill tensor of the foliation, or of the locally defined submersion.
So do you care at some point with the sign of the curvature somehow?
No, this is independent of the sign of the curvature. This is completely general. Yeah. So this is simply the tensor that tells us how far the horizontal distribution is from being integral. So how far this whole foliation on local submersion is from being a product. So this tells us how twisted the foliation is in some sense. And this is simply the torsion on the leaves and on the local leaf space. Okay. So what is the point of all that? Well, we have a geometry of Taoist to torsion. We want to understand it better, so we want to reduce it to smaller parts. There is no Iran decomposition theorem for these, as there is for Riemannian manifolds, because even if you have a reducible polynomial representation, or a reducible representation of H, the torsion does not need to respect this decomposition. So this is why there's a need for such a more involved principle. But you still, if you do this, you have your foliation, you have your leaves, which are naturally reductive. You can say, okay, I understand these fairly well. When you look at the local leaf space, and this indeed splits into irreducible geometries. And now you have the hope of classifying these irreducible geometries, which brings me to the work that has begun with Clayton and Schwahn. So this is a similar name to me, but he is not me, in 2004, when I was 5 years old. And recently, work by Moroianu and me, we classified the PST geometries, which are irreducible for H, and in particular for the stabilizer, because H is contained in the stabilizer. Let me just walk you through this a little bit. So we basically have 5 cases. Some of these were overlooked in the original classification by Clayton Schwahn, which is where we had to fix it. There are homogeneous spaces which are isotropically irreducible. So this means that we are in this case here, but M is an irreducible representation of H and not symmetric. We have these things, so here we have the canonical connection. We have these spaces here, which I talked about in example 3. So these have the Schwahn family of connections. We have the 2 exceptional cases of 6-dimensional nearly Kerr manifolds and 7-dimensional nearly Kerr 2 manifolds, which are well liked among people who care about killing spinners and such things. And then there's just generic 3 manifolds, which also appear. Here you can always take this connection, you take the tau to be some multiple of the volume form, and this will always have parallel torsion. Because the volume form is parallel for the Levi-Schlieder connection, so it is parallel to this connection. And so this is kind of trivially true. In each case, H is driven by that. So here it's the isotropic group, here it's H, here it's SO3, G2, and here's the whole SO3. And then you can ask, okay, if we fix H, what are the possible holonomy groups, the stabilizer groups? The stabilizer group is almost always the same as H, except for this curious case, which is the Bezier space, which is a very fascinating example in geometry. This is the homogeneous space SO5 modulo SO3, where this SO3 is embedded by its irreducible 5-dimensional representation. So this is a 7-manifold which has a nearly parallel G2 structure, which is also why it also appears here. Just as a curiosum. So for the monomy, there can be many things happening. It can be generically equal to H, or you can have some subcases. These would correspond to particular geometric situations. For example, here you have S U2 U1. If you have such a monomy reduction, we prove that this corresponds to M actually being a twistor space of a self-dual Einstein 4 manifold. So there is this twistor space constructions, and they always carry a Kähler metric, and if you rescale it with also a nearly Kähler metric, and this is this nearly Kähler metric here. So we get sort of converse results to some constructions in Barbaro-Pediconi geometry. Here, if we have a G2 manifold, then it probably reduces to SO4, then we know it's actually 3 other than Sasaki, and such things. Here for SO3, we have a relation to U1, we have something we know is alpha Sasaki. So there's a parallel vector field. Okay. So you don't need to get this table by heart, you just need to know that we completely understand these stabilized and irreducible, or these H irreducible pieces. and they don't pose any more problems now.
Sorry, Paul?
Yes.
Can I ask you a question? For different age, I mean, between the holonomy and the stack, you get different foliations, different submersions?
Yes, you can get, depends on age, what foliation you get. For example, you can take, if you start with a three-society manifold, you can take H to be just the holonomy group, then you get a foliation over a quaternion planar manifold, so we have three-dimensional leaves. But you can also take H to be something larger, such that it only sees one vector field, only one parallel vector field as a reasonable representation. And then we get a foliation with one-dimensional leaves, which is over a twistor space. Right? It's the twistor space of this quaternion planar manifold. So, or before, I should say.
Is there a preferred one with respect to the parallel scale torsion?
It depends on what you are interested in. I guess the holonomy is typically the preferred one. Well, sometimes you don't know what the holonomy is a priori, and then you have to fix some age, and then this makes more sense to work with that.
So did I understand correctly, then the foliation can be singular even?
Yes, it can be highly singular. We only know what it does locally, but globally it can be completely wild. For society manifolds, there is no need for these leaves to close out globally.
Oh, so the leaves might be eaten open?
Yes. Wait, no. Yeah, it might be. Or, I mean, dense. It could be dense.
Yes.
Yeah. Okay. So the question that we wanted to answer really after completing that is what if we additionally impose that the torsion is closed, so d tau equals 0, right? So then, just to see this from multiple perspectives, if we have a geometry with torus torsion, T is T, then the following are equivalent. D tau is 0. Actually, tau is parallel not only for the connection with torsion, but also for the Geneva connection. The curvature of the connection with torsion satisfies the first Bianchi identity, so it has the same symmetries as the Riemannian curvature tensor. For all x in tangent space, tau x actually annihilates tau itself. So that means that tau x itself is in the stabilizer algebra tau. And equivalently, the torsion satisfies a sort of Jacobi identity. So at each point, tangent space with the metric and tau defines a metric Lie algebra. So, as a definition, these are called geometries with parallel, skew, and closed torsion. So I will just write this abbreviation, Schwahn. So these geometries have been briefly studied by Agricola, Ferreira, and Friedrich, 2015, and they gave a partial splitting principle for those and a partial classification of the, or sort of a classification of the Riemannian irreducible ones in dimension at least 5. We have cleaned this up a bit and made it close some gaps. So if you want to know what the irreducible examples are, just check this table here of PSC ones. which ones have closed torsion. So it's the case for these Katzarkov connections and also for the free manifolds. So we know what the results are. They are quite boring in themselves, to be fair. So that was kind of a consensus until recently that these PCST geometries don't have really much to offer. But this has changed because it has been found that even a reducible PCST geometry might carry a geometric structure which is irreducible in the sense that it does not respect any splitting or any representation of the holonomy. So, so one paper is by Barbaro-Pediconi-Tardini in 2024, where they looked at PCST Hermitian structures. Hermitian PCST manifolds. These are also called Bismuth-Kähler-like, because the Bismuth connection is the PCST connection. So the splitting principle for PCST manifolds luckily does not need any of this complicated foliation stuff. So this was done, which is well names particular, Reva, and Friedrich, 2015, and also some additions to us. I'm mixing up the letters. PCST should be PSCT. Any PSCT geometry locally splits. And tau is locally isomorphic to the product of MEGI and tau I cross some Euclidean space with zero torsion across some irreducible Riemannian factors. So these are stabilizer, irreducible, and have non-zero torsion, so they are the ones which are in the table here. This is Euclidean and flat, and these are irreducible, non-flat Riemannian manifolds. And you can also write down what the holonomy is. The holonomy is a diagonal sum of the holonomy algebras of these connections here. Here we get 0 k times, and here we get the holonomy algebras of the Riemannian connections, of the Levi-Civita connections. Time? Okay. Perfect. So, yeah, so far so good. We have a fairly straightforward way of splitting those into irreducible pieces. And now we can ask, if we have a PCST geometry, what are the G structures, the geometric structures that they can carry, which are parallel under this connection? For example, the Hermitian structures that were studied by these three authors. So, question which G structures are parallelized by a PSCT connection. In many cases, if we fix a structure group G, such as UN or SUN or SPN or G2, it is actually the case that if they are parallelized by a connection with skew-symmetric torsion, then this connection is unique. Then this is called the characteristic connection. So in all of the cases we're going to consider this is the case. So we can always just say the G structure itself is PSCT, which means that the G structure has skew-symmetric intrinsic torsion, and the connection you get from that has, well, it is parallel and closed, the torsion. So we are going to focus, we looked at this for G in the Berger list of irreducible non-symmetric Riemann holonomies. So UM, SUM, SPM, SPM, SP1, and the exceptional ones G2 and spin 7. We also looked at it for spin K structures, for K at least 8, which are defined similar to spin 7 structures, just because out of curiosity. But in this talk, I'm going to focus only on UN structures because this is where the most interesting stuff happens. So this is all the case that they studied. So, as a recap, so let's ask, okay, what kind of UN structures are PCST? So the question would be, if we have such a 3 structure, what are the possible torsion classes? For PSCT UN structures, so almost Hermitian structures. So as a recap, what do I mean by torsion classes? So there is a classification by Gray and Galea, classification of possible torsion classes. So the intrinsic torsion that Enrique mentioned in his talk yesterday of the UN structure, it lives in the space, or it is can be thought of as a section of Tm tensor the orthogonal complement of UN in the bundle of 2 forms, so it looks like that. Somehow, right, you have the real 2 forms of type 2,0 plus 0,2. And this thing here splits into 4 classes, or into 4 irreducible components, which we can call W1, W2, W3, and W4. So W1, these are just 3 forms of this type, 30 plus 03. W3 are 3 forms of the other type, but trace-free. W4 are also again 3 forms, but so they are also of this type, but they are the trace parts. So they are like Tm, which the fundamental 2 form. And W2 is something that is, well, the complement of all those in the standard product. So this is the notation for these irreducible representations, and we say that the geometry is of Gray Abela class W1, for example, if the torsion is a member of this irreducible representation. So, for example, if the torsion is in W3 plus W4, this is the case if and only if the UN structure is integral. So if it is a bona fide Hermitian structure, right, the manifold is complex, not just almost complex. W1 plus W3 plus W4 means that it has skew torsion because these 3 are exactly the components of lambda 3, and this W2 does not appear in lambda 3. What else do we have? W1 plus W2 plus W3 is equivalent to being semi-scalar, which means that the fundamental 2 form is coclose, and W1 is equivalent to nearly scalar, which means that the nabla omega is a 3 form. So, yeah. alpha G omega is. And there are many other names for different combinations of these representations, but these are just some examples. Right, so the theorem of Barbaro-Pediconi-Tardini was, maybe I should first write the general theorem. So let me erase that. So I'm gonna explain how a general, almost Hermitian PSCT manifold looks like, and then I'm gonna tell you what possible torsion classes are appearing in this, and I'm gonna wrap up. So the statement is as follows. So theorem, if MGT is PSCT, J is an almost Hermitian structure or a complex structure such that it is parallelized. Then the manifold locally looks like this. So what we have H, GH minus 1/2 sigma. So this is a Lie group, a reductive Lie group with the Cartan-Schwahn -1 connection. We have, so because this is the torsion of this, so sigma is the canonical free form, this is the torsion of the -1 connection. We have a product of SI GI, the torsion alpha I vol GI. So these things are three-dimensional, alpha I Sasaki manifolds, and their real vector fields, which are the vector fields parallelized by the connection, we call them psi I. So these are vector fields on SI. And then we can also have a Kähler vector. So this has zero torsion. And J is the following form. J has to preserve the following spaces. Psi I perp in TSI, so this is a two-dimensional space, or two-dimensional spaces. Then it preserves the sum of H plus the span of all these real vector fields, and also, of course, preserves the tangent space of N. So the complex structure can mix these factors here. This is the important thing. We have this nice splitting into fairly well understood up to the Kähler factor manifolds, but the J does not respect the splitting. The J mixes all its stuff around, at least in parts. So, if we want to restrict our attention to Hermitian structures, so as before, M, G, T, and then let's say J is Hermitian, so we are in the torsion class W1 plus W3 plus W4, Hermitian PSCT, which are also called Bismuth-Kähler-like, BKL. Then it is as before, plus there exists a Cartan subalgebra, T in H, Cartan subalgebra, such that J preserves what now? It preserves the sum of T plus the span of the psi I. And it projects to an integrable complex structure on the flat manifold H modulo T. And actually, there's also the converse direction. So this means that every such product here, where J satisfies these additional properties, is actually PSCT and Hermitian. So they completely classified these kinds of manifolds, these Bismuth-Taylor-like manifolds, and we generalize this to the non-integral case. So yeah, these are the Hermitian manifolds. You can ask about other torsion classes. I'm going to keep this brief. So let's assume that the dimension of M is at least 4, because in dimension 4 the classification degenerates of Taylor and Abea. So theorem, if mg tau j is PSCT in W1 plus W4 or W3, then it is Taylor. So yeah, these special torsion classes cannot happen. More interesting if we have W1 plus W3. So this means that we are semi-Taylor with W2 removed. So this is the intersection of those two classes, semi-Taylor and skew torsion. Then what happens? Then locally mg tau looks like this. So again we have the Lie group factor, and we have the Taylor manifold. So there are no Sasaki factors appearing, and also H is not isomorphic to SU2 plus R. And conversely, so the converse is also true. If we have such a product where H is not SU2 plus R, then we can always find a W1 plus W3 PSCT almost Hermitian structure. So for this you actually need to do a bit of constructions, like doing really leaning heavily into the Lie theory of H, like doing some things with root spaces and all that. Yeah, but we actually can construct these things. So we can these manifolds are classified now. The J's themselves are not classified. You can have many. You could actually have several of these almost Hermitian structures on such a manifold, but at least we know what the manifold looks like, and we know that because this is the number minus connection, the J is left invariant. So there are not so many degrees of freedom. It's relatively confined. So yeah, those are the torsion classes for UN structures. We did the same things for other things in the Berger list. And there the upshot is that basically you can, it's always also of this form, even without any restriction on the torsion classes. So you get more explicit results there, but also more boring manifolds in a sense. So this is why I chose to showcase UPenn, because more interesting stuff happens there. So yeah, thanks for listening.
Any questions?
Earlier in the classification, I think it's about Lie-theoretic, it's the W1 type. There were twisters of Taylor with the inverse complex torsion type. So do they appear in your constructions at all or not?
Well, they don't have closed torsion. Well,
yes, but they probably have parallel torsion, no?
They do, yeah, they appear here. They are the...
But they're not dimension.
What?
They are arbitrary dimension. It's twistor space of Taylor with...
They can have an element, yes, true. No, they will not be... And I'm not sure if they actually have tutorial. But I mean, there's this cohomology manifolds. You have some sort of also reduction theorem that you can literally split them in factors which are well understood. And so I think it was like you have factors which are homogeneous, so three symmetric spaces and some other things. And then there's one class which is in 6 dimensions where you can have non-homogeneous spaces. So I guess everything that's homogeneous is already included in here.
But these systems are a priori not homogeneous.
No, but I mean you can. Yeah, no, true, yeah. Yeah. No, they're not. Yeah, I mean no, that's a good question. If they are really geometries powered skew torsion, then this foliation thing should apply. So yeah, you could ask how do these foliations look like for general unique elements. Yeah, that's a good point. But are you sure they have parallel skew torsion?
It was
Okay.
20 years ago.
At least they don't have killing spinners. At least that. It might have. I'm not sure if the torsion is. Yeah, I have to check. But yeah, it's for asking. Good question.
Other questions?
I have a naive question, just to see if I got it right. There in your first theorem, the general decomposition, you're assuming that in the middle.
For the almost middle ones.
Yes. There you assume the nullity of j equals to 0, right?
Yes.
And is that the same as asking j to be in the class 1 through 4? You're already leaving your j there?
Yeah, by virtue of this uniqueness result for unit structures, that if they are parallel by connection with skew torsion, then this is unique, so the intrinsic torsion of J is also skewed. So yes, this is sufficient, or it's equivalent basically to W1 plus W3 solution.
Thanks.
And now, please.
Mine actually is a comment. I was trying to solve a problem related to this in the G2 case, but in the very end of last year, Georgios Papadopoulos solved the entire classification for all the groups in the version list.
Yeah. Oh yeah, I should have mentioned actually this. I know this people have Papadopoulos, and there's actually a mistake in there. So he assumes, so I erased this already, that the statement that you have at every tangent, every point, the tangent space is a metrically algebra, and the algebra structure is parallel. So from this he concludes that the manifold is a Lie group, or like locally a Lie group at least. But this is not true. As we can see here, we can have these three-dimensional factors which do not have any Lie group structure whatsoever. So he misses those. His results about G2 and spin 7 are correct, however. So we reproduce them. There are no three-dimensional factors there. Sorry, there are, but they don't. They are S3, so they are Lie groups. Yeah.
The questions or comments? Well, let's move forward. I guess there's some comment. Yes. Yeah, there's some comment. We have Donato from ICMS Sofia, but David is really from here in Camp. It's going to speak to us GKM approach of like that. So there's Giovane.
So the idea here is to study flag varieties, but from the point of view of Gromov theory, atom theory, and try to give away the first goal. The talk is we're trying to give away, not try to give away, to compute Gromov invariant and quantum cohomology for flag varieties, and the second part is to use that theory to compute the same things, but for complete intersections in flag varieties. And we do so by using this GKM approach that I'll explain what it is. But let's start from the beginning and define what is the Gromov invariant, or this Gromov theory. So, well, from the lecture, we have here X has smooth projective variety, so you can think of a scalar manifold as well. And we have a class beta in the second cohomology, there is an effective class, and we define what is the modular space of stable maps. So, we start with what is a stable map. So take a curve C, let me. So a G0 stable map is a map from a curve that possibly has some nodal singularities. So something like this, we have curves that can have nodal singularities, so things like this. Right? It has some market points, so we can just mark some points here. So let's say x1, say x2, say x3, things like that. And we have a morphism to a variety x here. So this is a stable map. Of course, they're also requiring here genus 0, so it kind of forms this tree. It doesn't have genus, so it doesn't have like cycles and things like that. Just form this kind of tree of, and each of these guys is a projective line, so P1. Right?
So when you say smooth mark points, you mean the mark points are not on the nodes?
Sorry, say that again.
When you say smooth mark points, do you mean that the nodes, the mark points can't be on the nodes?
Yeah. And the test for stability condition, there is the automorphism group of this map is finite. Okay? And we define what is the modular space of stable maps with genus 0 and mark points and the chosen homology class beta to be the space of all such maps, such that the push forward of the fundamental class of the curve is the chosen beta. Right? So this defines what we call a delineating movement for the stack. And that's interesting for this reason. So this is not a very nice space. So it doesn't have, say, a fundamental class in which we can do integrations and things like that. But it does have a virtual class. So it's some cohomology class that acts like a fundamental class in which you'll be able to integrate over it. And using that, then we define the Gromov invariants. So first define what is the evaluation map. So you just pick an element of the modular space of stable map, meaning just one guy like that, and evaluate on one of the market points. Okay? We can do then pullback by this map. Sorry, it's a Brazilian common mistake. Okay, so we can do pullback by these evaluation maps. And so given n cohomology classes, we can pull back each one of them, make the curve product of them, and integrate over the virtual fundamental class. And this is what we call the invariant Gromov invariants. Sorry, the Gromov invariants. Alright? And these are the guys that we want to compute for flat varieties. In general, this is something very hard to compute. So that's why we use this kind of GKM approach. I should also say, like, intuitively what this is trying to compute, right? So, say these cohomology classes, they come from the cohomology of some subvarieties. This tries to compute the amount of rational curves that passes through these subvarieties in their general position. So intuitively, that's the idea of the Gromov invariants. They work very well in enumerative geometry. Okay, but before we move on to the actual computations, let me tell you also what we want to do with this Gromov invariants. That is to do quantum cohomology. So we define what is the Gromov potential. given a cohomology class gamma, we define the Gromov-Witten potential of that to be this guy. So the sum over N of the Gromov-Witten invariants of any copies of gamma. Alright? So we're summing here of On, meaning this is a formal power series. It doesn't have any convergence results, general convergence results, just a formal power series on this on N. Okay? This is a nice and clean expression, but it's not a good expression if you want to do actual computations. So for that, we will open everything in coordinates. So pick a basis for cohomology. So like T0 for the would be the identity, a basis for H0, and also pick a basis for H2, the second cohomology, and pick a basis for the complement of your cohomology. So we can write any cohomology class in coordinates. So instead of writing gamma as a cohomology class, we can write it in coordinates of this picking basis. And we can use some Gromov-Witten invariance axioms to open up this expression and get something like this. So the Gromov-Witten potential is the sum of these two guys, what we call the mathematical part. There's just the normal product integration over x, and that's classical, and we call the quantum part, where these are the Gromov-Witten invariants of the elements of the basis, and these are the coordinates. Here appear the coordinates of the chosen class gamma in which you took the Gromov-Witten potential. Okay? This is the expression I usually tend to do computations just because everything is opened up, but it doesn't have to be. I know it's big, but it's an easy expression to work with. If, and here's the tricky part, if you can compute the Gromov-Witten invariants. Of course, it's still a formal power series. So, what do they do with this? We can define the quantum product. So, just define first this G matrix here. The Gij would be just the integration over X of the Ta and Tj elements of the basis. And we define the quantum product in the basis that we chose by this expression. We take the Gromov-Witten potential that we constructed, we derivate, we take the third derivatives and define by this expression. So this is what we call the quantum product. Like I said, the Gromov-Witten potential depends on the chosen class gamma. So this depends. The quantum product depends on a cohomology class, and depends on the cohomology class that we chose to construct. Okay? And again, this guy is a formal power series. So the output of this formal is not at one cohomology class, it's a cohomology class times a formal power series. So we just extend this definition so it makes sense. This definition is not a map on the cohomology to the cohomology, right? So we extend the cohomology tensor the ring of formal power series. Okay? And we define this by this is the quantum cohomology ring, and inside this operation is well defined.
There is a typo, it's like a few double brackets. When you say
yeah, it should be double bracket. Yeah. We missed it. Yeah, here it should be the double bracket, meaning this is an algebra over the set of formal power rings, formal series in these coordinates, the coordinates that we chose for this. Okay? And this, in fact, we have the identity of the cohomology still an identity in the quantum product, and this operation is commutative and associative. Okay, why are we interested in this MIG, HPs? No. want to compute atoms. And Leonardo has talked to you about atoms, and many others will talk about it, and Ludmil has talked about them. And you notice that everyone will talk about atoms in a different way. I'm more focused here in how can we compute them. And here are what atoms are in a simple way, let's say. Don't give me Ludmil for simplifying this too much, baby.
Like you I did even worse.
So we want to look at this operator, an Euler vector field, quantum product with a class gamma, and this gives us an operation in the quantum cohomology ring. So it gives us a linear function in a quantum cohomology ring. This Euler vector field is given by this expression, so it's the first term class plus this term here. And the idea is that, so all of this depends on the class gamma that we are choosing to do the quantum cohomology. We want to vary this class gamma and look for the gamma that will give us the maximum amount of eigenvalues for these linear operators in the quantum cohomology. So when we find this gamma that gives the maximum amount of eigenvalues, the eigenspace decomposition is what we call this local algebra, or an atomic representation. Okay? Any questions? But let's first simplify this matter, because this Euler vector field has somewhat complicated expression, and working with formal power series is a hard task. So what we want to do is what we call small quantum cohomology. So the quantum cohomology depends on the class of the cohomology class that you choose. So if you choose a cohomology class in H2, we get what we call the small quantum product. And what makes things easier is because now we are not working with formal power series. This is a finite sum. So the small quantum cohomology is given by this expression. We only have Gromov invariant of 3 elements, and we still have the variables of H2, of the elements H2, but all the other coordinates, all the other coordinates that appear for the other elements of the base, they do not appear here. Okay? And this is, like I said, a finite sum, so it's something that we can actually compute all of these guys and have an answer. Okay? Well, let's do that for flag varieties. That's the main goal of our project here. The first goal for our project. So let's define what is a flag variety. By flag variety, I mean a complex of homogeneous space, where G is a connected, simply connected, semi-simple complex Lie group, and P is a parabolic subgroup, meaning it contains some border subgroup. You can think of border subgroups as the set of triangular matrix in your group, right? And a parabolic subgroup is something that contains this. I'll talk a little about flag varieties, but the main idea here is to say that all of the geometry of these varieties is encoded in a combinatorial set of the root space decomposition. So let me define this. We call some linear functional on the torus. So every, because it's simple connected and everything group, we have a maximal torus, right, on it. So we can take the algebra of the torus and look for linear functionals on it. And we call a linear functional a root if it satisfies this expression. You have some linear subspace here, non-zero linear subspace. That's the bracket of guys in this space. It's just applying these linear functions. So basically, a root is a linear functional that operates as an eigenvalue for the adjoint representation in the Lie algebra. Okay? And then, where it begins to become interesting is that this gives us a decomposition of our Lie algebra. We have here the algebra of the towers, plus all the root spaces that we constructed. And we denote by R the set of all the roots. So, all the geometry of flag varieties is contained in these constructions, in this root space decomposition. Right? So let's give an example of this just to illustrate. I'll call FL3, and this is an example that I will use to explain all the concepts that work here. This is just the group SL3, meaning the 3x3 matrix of the determinate one, quotient by the Borsov group, meaning the matrix of upper triangular matrix. Okay, there are many other ways to see it as to visualize this space, like this set of full flag in C3, meaning pairs of subspace 1 and V2, V1 are one-dimensional subspace, V2 are two-dimensional subspace, one containing the other, and this all the pairs, all possible pairs that satisfy this is the space of full flag in C3. Or you can also look at it as the projectivization of the tangent space of E2, or you can also look at it as in coordinates. There are many ways to look at it, but the point is that we can use Lie-theory, we can use the root space decomposition to encode all the geometry. And this is the roots of this space. We have two simple roots that we call alpha and beta. They are the roots that they work as generators for the whole root space. And we have another root that is just the sum of these two roots. So most of the time, the actual definition of who these guys are doesn't come. It's not necessary. Most of the time, just is the combinatorial. Here, meaning you have two simple roots, and one root there is the sum of others. Of course, these are just the positive roots. If you take the whole roots, would be also the negatives of these ones. Right? Before we move on to actually doing geometry here, I just want to talk about one more combinatorial set in flag varieties. So this also, like I said, the root space decomposition encodes all the geometry. But you can take this root space decomposition and construct other combinatorial sets, like the Y group here. So the roots, they're linear functional on the torus. Linear functions, they determine hyperplane on the torus, meaning you can talk about reflections on this hyperplane, right? So the Y group is the set of the group generated by the reflections of the simple roots. All right. So for example, for FL3, we had two simple roots. So the Y group would be the group generated by the reflections of these two simple roots, the reflections in these hyperplanes. Of course, this will not be an infinite group because they are reflections, so you have some relations here. For example, if you do reflection by one root and then reflect again, in the same hyperplane, you get the identity, and you also get other reflections. So in the end, this will be a finite group. In this case specifically, you have these two. These will be divided with the identity, the two generators, their compositions in both ways, and this maximal element, which is composition of the red. This is isomorphic to the reflection group S3. Well, let's see how the geometry is encoded in these guys. For example, we can look at, we can construct a basis for cohomology from this. So pick an element of the Y group, here W. We can define the Schubert variety by this. You take you can look at the there's a way you can look at the Wien group as a subgroup of a group G. So it makes sense to look at the base point W in the homogeneous space and take the orbit of the Borel subgroup. Here just conjugates the Borel subgroup, so every dimension works nicely, but it's not really necessary. So you're taking this orbit of this conjugation of the Borel subgroup of the base point W. Take the closure of that, and this is what we call a Schubert variety. Okay? So if you take the cohomology classes of these guys, what we call here sigma W, they give a basis for cohomology. Sigma W is in the cohomology of 2 times the length of the Wien group. And by length here I mean the Wien group is generated by synchro reflections. So the length is the amount of reflections you need to achieve that. Okay? And it gives a homogeneous basis for cohomology. Okay, good. So, in the example that we're discussing, we had 6 elements in the Wien group. We had the identity, which of course has length 0, so it's a basis for H0. We had 2 generators, S alpha and S beta, so they're Schubert's classes. Generates H2. We have the guys S alpha, S beta, and S beta, S alpha. They have length 2, so they form a basis for H4. And we have also this maximum element here. There's a class of a point. There's a basis for H6. So the Wien group will give us a basis for cohomology, and you can also see here the Hodge diagonal would be 1, 2, 2, 1. Okay. Alright, so let's now create a way to compute Gromov invariants, and you do so by using GK theory. The idea here is that computing Gromov invariants is a hard thing, partially because the moduli space of stable maps is complicated sets. So we'll introduce some torus action that will allow us to simplify this moduli space of stable maps when you look at only the fixed points by this, and parameterize the fixed points of the moduli space. Okay, so what is a GKN space? So we have here an algebraic torus and a Schwahn projective variety, and we put an effective action of this torus in the variety. We'll call this a GKN space after Goretzky, Kottritz, and McPherson if the fixed point set is finite and the one-dimensional orbits, meaning the orbits that are one-dimensional, they are isolated. Okay? So a flat variety is a GKN space because we have the maximal torus is a subgroup of the group G, so it acts by, well, just multiplication. Okay. In GK theory, you're also interested in, you have the same idea like variety, that is to encode the geometry in a combinatorial set. For GK spaces, you have the called GKN graph. So given a GKN variety, you construct the GKN graph where the vertices of this graph are just the fixed points, and the edges of this graph the edges of this graph are the closure of the one-dimensional orbits. Okay? So, for flag varieties, for example, how would we construct this graph? We can show that the fixed points of the maximal torus action are given by the elements of the Wien group. So, like I said, the Wien group can be seen as a subgroup of G, and the fixed points would be just the elements of the Wien group. And what are the one-dimensional orbits? So, given an element of the Wien group, meaning a fixed point, and given a root, you can construct a group, a subgroup of G from this root that is isomorphic to SL2. Okay? And when you take the quotient, the quotient with the model subgroup of the parabolic subgroup, if you're in non-maximal variety of these guys, this will be isomorphic to a P1, a projective line. Okay? And these guys will be the one-dimensional orbits. This is an easy computation to show that these are the fixed points and these guys are the one-dimensional orbits. Okay? So in the example that we're working on here, this would be the GKM graph. So, like I said, the fixed points are given by the elements of the file group. So we have 6 elements in the file group. These are the fixed points by the torsion section. And at each point, every root will give us a one-dimensional orbit. So every root will give us an invariant P1 line. So for example here, we have 3 roots and we have 3 invariant lines connecting to 3 different other invariant points. Alright? Alright, so let's see how we can then compute the Gromov invariance with this. We have, so if you're in a GKM space, we have a torsion, right? So we can induce a torsion on the modular space of stable maps. We do so just by composition. So, like I said, modular space, element of the modular space of stable map is a map from a curve to our space X. So you just multiply here by the torus. You just add to here with the torus. Okay? How will this simplify things for us? These guys here, these curves and these maps, they are not easy to parameterize. But if you're now looking, if you start looking now only for the fixed points of this sort of
PI, are they fixed or what?
Which fixed?
PI.
PI?
The market
Oh, the market points. Yeah, they...
I mean, the torus doesn't act on the curve, right? So the points are marked on the curve.
So did you assume that your curves are already marked on X or just...
I assume that the curves... The market points are on the curve.
So you don't fix them out on X?
No.
No, but...
No, that's what it is your choice you're going to do, right? You're going to choose where to send the market points, right?
Yeah.
It comes up posteriori.
But they will have to be fixed by the torus action if you're looking at fixed points. Otherwise, you're looking at different curves. Yeah, so how do we parameterize the set of fixed points? Yeah? So, if you're not in a GKM space, we have a GKM graph inside this guy, meaning we have fixed points, let's say we have something like this, we have fixed points, and we have invariant lines that connect these fixed points. Let's say the GKM graph of this variety was something like this square. We have fixed points, and we have invariant lines. For these guys, like this curve is meant to be invariant, we have to map all of this curve inside of this. Okay? So the singularity points have to come to the fixed points. The lines have to come either to lines or they have to collapse to points. And four things have to happen. So the only restriction that appeared is that things like this cannot happen. We cannot have lines with... Sorry, the things can happen, but things like this have to be mapped to a point. They all have to collapse to a point. Right? So this is the only restriction that appears. And this is important because this will simplify very much what can happen here. Sorry?
If you have this circle,
Yeah,
there is
they don't have to connect to a point.
Then sure they don't. They have to align.
So the singularities, they have to be mapped to fixed points.
Yes, but not the.
So you don't have 3 fixed points in a line, right? So you have a line here, you don't have 3 fixed points.
I agree for this, but not this. You just have to circle the one component, not two.
You mean that this guy could be...
This guy doesn't contract. Yeah. Otherwise, it's not stable. Because it's a P1, so it cannot contract.
Yeah, I'm not looking at stability. Of course, you have to satisfy all the stability conditions.
This line, this P1,
Yeah.
that's to a line. To a line in X, not to a point in X. That's just what I want to say.
It's because it has only one special point. Right?
Yes, it can happen.
So it happens.
Same
Like
happen.
what you draw on the blackboard here doesn't happen. That this line mapping to a point, no, that's not possible. Because it's not a stable.
Yeah, I should say, I drew this. I really didn't think about the stability conditions. You could have other things happening here, as well. Just a drawing to illustrate. Of course, you have to satisfy all the stability conditions.
Just mark 2 points and we'll be fine.
Yeah.
No, because there's
You have similarity.
Yeah, the node plus 2 other.
Yeah.
Yeah.
Yeah, but just like this P1 with just one node. These are also important in your computation now. And they map 2 lines.
Yeah.
Alright, but simplifying things here. If we have this guy, we want to parameterize the fixed point. And what I do is, this looks very much like a graph. This is very close to a graph. So we will look at this now as a graph. So meaning, just correct this node of singularities, just move them out. Anything that gets collapsed to a point, so say this is collapsed to a point, just collapse them to a point. We have something like this, like we said, this could be mapped not to a point, right? So just moving things out, the curve that we drew can become this graph, okay? With the market points that we have, and like I said, every vertex here, meaning every singularity, has to be mapped to a fixed point. So they have a market fixed point here. So let's say this W1, W2. Every singularity here is marked to a point. Every line is mapped to a line here. So if this is L1, we have the line in which this guy is being mapped. Alright? So we have all this information. We have the market points. We have the points in which the singularities are being mapped. We have the edges in which the edges are being mapped. Alright? And all this information encodes all the possible fixed points. So now if we vary all of guys that can be constructed in this way, meaning I can construct all trees with all this information, so telling which point, to which points they are being mapped, to which lines they are being mapped, telling where are the fixed points. This parameterizes the set of fixed points. Alright, so let's do this a bit more formally. We call a market tree would be a graph. So with a set of vertices, a set of edges, then we have to be a tree, and we put all the information here. We put marking points, so like the marking points of our stable map. For every vertex of this graph, we correspond to a fixed point in the GKM space. So for vertices, we correspond to a fixed point in which it's been mapped. And for every edge, we correspond to an invariant line, an invariant one-dimensional orbit, which is just a one-dimensional orbit that it's being mapped. And we also encode the degree of the action. So this guy is isomorphic to a P1, and it's being mapped to a P1. You can look at the degree of this map. Alright, so this is what we call a marked tree. And like I said, we can, for every fixed point of the modular space of stable map, we can construct such a tree in this way. And we have that they're in bijection. All the marked trees that can be constructed with all the information are in bijection with the modular space, the fixed points of the modular space of stable maps. So why this is interesting? Because we now have this way of encoding the modular space, at least the fixed points. And we can use this to compute the invariant Gromov-Witten invariants, meaning we can compute the Gromov-Witten invariants when we are encoding the torus actions on the space. Okay? And this is the formula we propose for doing so. So don't get scared by it. It's an ugly formula, but simple to understand. So just pick some invariant splitting of your invariant cohomology, and now let's compute Gromov-Witten invariants. So pick some cohomology classes, some class beta. Then we have that the equivalent Gromov-Witten invariants of these guys are given by this formula, where here we're taking the sum of over all marked trees that are constructed this way. So, but now we're just asking that they have cohomology classes beta, meaning each edge, the sums of over the cohomology class of all the edges will sum up to the chosen class beta. And we can compute what we call the weights of this graph, represented by this ugly expression here. So we sum up all of these guys, and here just the splitting the cohomology. We sum up all of these guys, we can actually compute Gromov-Witten invariants. Okay? So just to show, open up the formula, this is open up all the functions that we have in the formula. So it's a big expression, and summing over all graphs can get very huge. So this is something that is more suited for doing computations in a computer. And that's why we decided to use this and develop a software that does this. But this formula here, I decided we're going to compute Gromov-Witten invariant and flag varieties, but this formula works in general for GKM space. Okay? There's just one catch. All of these lambda guys that appear everywhere, they are the characters of the torus action. So in different vector spaces, so tangent spaces of the fixed points and some of them. So there are the characters of the torus action. And in a general GKM space, they can have very different appearances. So you can use this for any GKM space, but you need to compute all of these guys. The idea in flag varieties here is that we can write these guys in terms of the data of the variety. We can even, for general flag variety, any flag variety, we can write down how these guys will behave in terms of the root space decomposition. So that's what we did, and it's not 100% finished, but it's close to that. We're developing this software that can compute this Gromov-Witten invariants for any flag variety. You just need to input the cohomology class you want to compute, and the class beta. And of course, with flag variety we are working on. Here are some examples of that. This matrix is the two-pointed Gromov-Witten invariants. We just vary the Gromov-Witten invariant to the Schubert-Belling basis that I showed for some cohomology class. For this cohomology class, I didn't say this for the example I was talking about, right? Or this guy, the Schubert class of the first input. Okay, and you can do this for any Gromov-Witten invariants. So this is changing the beta. You can compute the Gromov-Witten, and we can compute for any flag variant, just not the example I showed. This for the flag variant SO5 over the bottom subgroup, can also do the same computations. And of course, if you can compute the Gromov-Witten invariants, you can compute quantum cohomology. Yes. We can compute any Gromov-Witten invariants, but if you want to finish it in finite time, we need to do this one. And for example, for FL3, we can compute the matrix of the quantum multiplication by the first term class. Okay? And we get this matrix here, where y1 and y2 are the coordinates, because if you remember, the quantum cohomology depends on a given cohomology class. For a small quantum cohomology depends on the cohomology class in A2, so it has two coordinates, y1 and y2. And we get here that we can have 6 different eigenvalues in this matrix if we take the coordinates one different to the other, and we have 4 eigenvalues if we take the coordinates one equal to the other. Okay? So from this, we know that the atomic representation for FL3 we have 6 different atoms. Okay? Because, like I said, the atoms are will be given by the atoms are when you take a cohomology class that gives you the maximum amount of eigenvalues. So here we already found 6 eigenvalues. So there can be no further splitting, there can be no more eigenvalues because the 6 is the dimension of the cohomology. So we already know that this is the maximum amount. This is the atomic representation of the local atoms. Okay, let's do a small tour before we. How much time do we have?
Like 3 minutes?
3 minutes.
Maybe 5.
All right, let's keep going. Let's move on to the most interesting part that I want to talk about. That is complete intersections. So just to define very quick what is a complete intersection. Say you are in a smooth projective variance X, and you have a vector bundle over it that is generated by global sections. We can take a section that intersects the 0 section transversely, and we can look at the 0 locus of this section. Okay? This defines a smooth reduced scheme, and the codimensional is the rank of the vector bundle that we chose. Okay? This is what we call a complete intersection. It's not working very properly. Okay, and now let's put the assumptions that we are working on. Let XPH move for sections GKM space. Have this vector bundle, and we can decompose this vector bundle at the fixed points of GKM of the GKM variety. Like this, and compute the weights, the characters of the torus section. Okay? We can use all of these and the Green-Crash-Pantev theorem to compute Gromov-Witten invariants in this class. So again, we have an expression for Gromov-Witten invariants in complete intersections. Okay? And this case is very interesting because in flat variants we know them to be rational. But complete intersections is a much more wider space. So here we can actually compute atoms and look for rationality or de-rationality or generalizability using this expression, which is basically the same that I showed before. We just added a correction term for the for the vector bundle that you construct. And just to show here an example of how this can be done. This is, let's see which example you want. Right? So in FL3, we can look at the complete intersection determined by the line bundle. There's the root of the anticanonical line bundle in FL3. Okay? If we do so, we will get this surface, the blow up of P2 in 3 points, which has these hot diamonds, and we can use a theorem to compute the matrix of the quantum multiplication by the first term class. And we get this matrix. And look, we can do this for many examples, for any complete intersection in flat varieties. And using quantum cohomology, we can try to argue about the atomic representation. Okay? Because doing the computations in big quantum cohomology is much harder. So what we do is we compute the small quantum cohomology and we try to argue in different ways why that's enough, why the small quantum cohomology will give us enough information about the atomic representation. Right? And yeah, we'll end here. Thank you.
Questions? Yes, please do.
During the implementation of your theorem, what is the main computational bottleneck you found?
Computational bottleneck.
Why did it take so long? What is the bottleneck?
Well, the set of graphs can get very big because you have so many information, right? So say you have edges. Say you want to make a computation, you have like edges up, graphs up to 5 edges. Okay? So this is already like not so big a space. But then you have to add the market points that can be everywhere. You have to add these markings, meaning for every vertex you have to attach a vertex of the decaying graph. For every edge you have to attach edge of the decaying graph. So the computations start to get, given one graph you have like 10, 20 market trees from that graph, and you have like 10 graphs, and things start to get big. That'd be what takes some time.
Also, maybe I want to say that something that we studied a lot is like there's no nice scripts to generate graphs, and so we have to do this from the scratch. And none of us is good with computer, so it takes some time. And then also, like after you do that, you have to be able to generate market graphs. There's no script to it for it. So it took some time also regarding this matter.
If you guys want, I can put some, because I don't know if you're familiar, but in the realm of machine learning, very recently a lot of computational techniques are being applied to help with very hard algebraic geometry computations. So there are a bunch of examples of very difficult scenarios where machine learning is being used to simplify computations of Hodge numbers whatsoever. And the general philosophy is to include just a very small subset that is representative enough of, I don't know, the sort of problem you're trying to approach. And then the machine tries to extrapolate these autonomously. Of course, there's a question. I mean, I don't want to take so long, but the thing is, if you are interested in talking about these things, I myself have been interested in different kinds of problems, but using those type of computational techniques. If you want to discuss a little bit more about it,
let's
try to give a little bit more inputs.
Let's discuss.
Any other questions? All right. Not let's thank Giovane again.